So now let's look at generalized Butler-Volmer equation. When we start to think about mass transfer limitation or mass transport limitation, when we start to think of concentration is no longer uniform at the beginning, which we assumed. Okay, so for a generalized one-step electrode reaction, or we call half-cell reaction, OX plus n number of electrons to form reduced species. The generalized Butler-Volmer equation that relates net current density J as a function of over potential for that particular electrode reaction or half-cell reaction. We said the over potential is the potential for the actual electrode reaction to occur versus the equilibrium potential for that redox or electrode reaction to occur. So, generalized Butler-Volmer equation that relates current density and over potential is given by this equation. J, the net current density, would be coming from two parts, JA plus JC. JA would be the anodic or oxidation component. JC would be the cathodic or reduction component. And the net, when you add these two together, net would be the J. JA, of course, as we said, would be positive for anodic. JC would be negative for cathodic. But then when you add JA and JC, that the overall number could be positive, then it means the overall electrode reaction is anodic or oxidative, or negative means the overall reaction is cathodic or reduction, or zero means there's no net reaction. It is under equilibrium. Okay, so JA would be J0 times the first term in the braces, and the JC would be the second term, J0 times the second term, and don't forget this negative sign here. And different from the previous Butler-Volmer equation, now we have a term called the CS over C0. CS over 0 for reduced species for the anodic component. So it's determined by the reduced species concentration ratio. And the CS over C0 for the OX or oxidized species limits the cathodic or reduction component. Okay, and as we said, explained before, JA would be anodic current density component. JC would be cathodic component current density. And both of these often in the unit of amp per centimeter square. You may come across other units such as amps per meter square. J0 would be the exchange current density. Which would be when the over potential is 0, then the JA and the JC value, that would be the exchange current density. And beta, as we said before, it would be a symmetry factor for the half cell or electrode reaction, and typically unitless. Quite often, beta would take the value from 0 to 1, and quite often it's 0.5. CS RED and C0 RED are the surface and the bulk concentration for the reduced species. RED again is for reduced species. C for concentration, S for surface, 0 or not for bulk or deep within the electrochemical system. Similarly, CSOX and C0OX are the surface as well as bulk concentration for the oxidized species, OX. OX for oxidized species, S for surface, 0 or not for bulk concentration. Okay, and then R, of course, would be gas constant, and T for absolute temperature. N would be the number of electron transferred, F would be Faraday constant, and eta would be the overall electrode over potential. Okay, so this gives us the generalized Butler-Volmer equation when we can no longer assume uniform concentration. There's no active stirring. The concentration from the electrode surface to the bulk is no longer the same. If it is the same, you see that the surface and the bulk concentration, if it is the same, then this ratio goes to 1. Similarly, this ratio also goes to 1. Then we have our original Butler-Volmer equation or simplified Butler-Volmer equation. But now, when we have to consider the concentration gradient within the system is no longer uniform, then we have this ratio to take care of it for both the reduced species going through anodic or oxidative reaction and for the oxidized species going through cathodic or reduction half cell reaction. Okay, so this we have the generalized Butler-Volmer equation. And with that generalized Butler-Volmer equation, if mass transfer is limited by diffusion only, then we can further get a little bit more information. J, again, we write that equation is J0 braces and the ratio, concentration ratio for the reduced species times exponential term minus ratio for the oxidized species surface to bulk times the exponential term. And then this ratio between concentration surface to bulk for reduced species, surface to bulk for oxidized species are for the anodic and cathodic process of the same electrode reaction. So when you write this Butler-Volmer equation, remember it is for the same electrode reaction, the same half cell reaction, not like in the full cell. You write this only for one of the electrode in a cell. Then the Cs over C0 for reduced species would be 1 minus J over limiting current for anodic, because reduced species going through anodic reaction or oxidative reaction. So this is what we obtained earlier if the mass transfer is through diffusion. Similarly, Cs, surface concentration to bulk concentration for the oxidized species would be I write it as 1 plus J over J limit C. Why do I write plus? Because if we are talking about cathodic reaction or cathodic process, then the J would be negative. So J is negative, but 1 plus this number will have a number smaller than 1. Still means the surface concentration is lower than the bulk concentration. Okay, so we keep this plus sign because we start to consider the sign convention for the current. J will be positive if it's anodic, so we take care of this one. But on the cathodic part, J will be negative, but this 1 plus the ratio will still be smaller than 1, from 0 to 1. As a result, if we have these two ratios specified in terms of current to limiting current ratio, then we can rewrite the generalized Butler-Volmer equation. J equals J0 braces, but the first ratio for reduced species would be replaced by 1 minus the ratio between current to limiting current for the anodic process, exponential term minus the surface to bulk concentration ratio for the oxidized species will be replaced by 1 plus J over J limit for cathodic. The plus again due to current would be negative if it's cathodic. Okay, and of course don't forget the exponential term. expand this equation, then we are going to have this long equation, J on the left, J0, 1, exponential term, we have it here, J0, J over J limit, exponential term, don't forget negative sign, become the second term on the right. So we rearrange J0 over J limit in current for anodic but times J. Then the third term, J0, 1, exponential term, okay, don't forget negative sign here. And then the last term, still J0, J0, J, J, limiting current for cathodic process, exponential term, but then 1 minus sign. So this is what we have. From previous page, we have this relationship. Now let's do one more manipulation. Let's put all the term with J, the net current density, to the left. So J term, the second term on the right, the fourth term on the right. So we are going to move this term to the left, the first term to the left of the equation, and this would be what we have. J, we have the minus become positive for the anodic process. The minus become positive, and then for the cathodic process equals, okay, exponential term J0 minus exponential term J0. Then we can get the net current density to be, this is our numerator, and our denominator will just be 1 plus exponential term, the ratio between exchange current density to limiting current density, plus exponential term, ratio between exchange current density to limiting current density. Okay, so with this equation, in principle, we can calculate the current density, the net current density, the net result from anodic and cathodic, from oxidative and reductive process for the same half cell or electrode reaction. If we know the overpotential, we know the symmetry factor, we know the number of electrons transferred and the temperature, then we can calculate it. Of course, sometimes people would rearrange this equation a little bit further and divide J0 for the numerator and for denominator. So J0, J0 gang, and this one become 1 over J0, and J0 gang here. So 1 over limiting current density, and 1 over limiting current density for the cathodic process, for the anodic process. Okay, so this is the equation that allow us, these two, either one you can use, to allow us to calculate net current density if we know the overpotential, we know number of electrons transferred, we know temperature, we know symmetry factor, we know limiting current density for both the anodic process and the cathodic process for the same electrode reaction for all the half cell reaction. Okay.